Hello everyone, welcome to Chemistry 1101, Introductory Chemistry for the Maastricht Science Program. This is our first lecture, our pre-recorded lecture that we're doing this particular year. And what you'll see is that this lecture will be broken up into 6 parts that all follow subject-related areas, and that way you don't have to watch one single video for an extended length of time. So we'll go ahead and get started. So we are going to start out talking about atoms. And the reason we want to start out talking about atoms is because I teach this course using an atoms first way of teaching. And so we're going to build up from our smallest particles, our atoms and our subatomic particles. We'll go from there to making molecules. Once we make molecules, we'll learn how molecules go together by bonding, so we'll learn about bonding. And then once we make molecules, we can start talking about reactions and some of the things that they do. So we're going to build up throughout the semester in our complexity. So we're not going to worry so much about chapter 1 in the textbook. I certainly invite you to read through that chapter. That involves a lot of things about measurements and some other material that we don't really have time to cover in this very abbreviated time for this course. So we're going to start in on chapter 2 talking about atoms. And so when we think about what matter is, well, we can have a lot of different definitions. One simple definition is we could just say that matter is stuff. And that's not a very scientific description, is it? Well, let's expand that one a little bit farther. We can say it's stuff that has mass and it takes up space. That's pretty much what little brothers and sisters do, isn't it? They have mass and they take up space. Well, again, not very scientific in our description here. And so we might want to go just a little bit farther. But now we start to see some of the challenges that people had in identifying matter centuries ago. Now, much of our matter is very easily identifiable just by using our simple definition of something that takes up mass or has mass and takes up space. Something like the table, the chair, any of your books, those kinds of things are very easily identifiable as matter. Something that's not very easily identifiable or easily detected would be something like air. It was a very long time before people realized that air actually had a mass. We didn't really feel it. And even if now you raise your hand up, it's not like you feel yourself lifting up the weight of the atmosphere, when in fact, when we're here sitting at sea level, or essentially sea level, if we were to lift all of the mass up in the atmosphere above you, for every maybe 5 or 6, maybe 7 square centimeters of space in your hand, it would weigh well over 50 kilograms. But you don't feel that kind of weight lifting with one hand, and that's because your air moves through it. So this was some of the difficulty in the past of identifying air as matter. But in fact, it is matter. It does take up space, and it does have mass. Now, anytime we're looking at chemistry, some of the things that we look at are physical transformations or chemical transformations. Now, during a chemical or physical transformation, what doesn't happen is the mass does not change. What that means is that all of the atoms that we put into a transformation must come out as well, and they cannot change their identity. They can change what they're attached to. However, any oxygen atoms that go into a reaction must come out as oxygen atoms, and the same with any other type of atom as well. Now, for a long time, atoms were believed to be the smallest particle that we had. And then sometime in the 1800s, in the 1900s, late 1800s, early 1900s, people started to realize that there may be particles that are even smaller. And these are called subatomic particles. Now, when we look at subatomic particles, we realize that they have masses as well. And we express their masses in things called atomic mass units. It's much easier than trying to state their mass in terms of grams. Now, these subatomic particles are extremely small, as you might imagine, and one atomic mass unit is equal to 1/12 of the mass of a carbon-12 atom. And we're going to see what that carbon-12 means here in just a little bit. Now, many of our subatomic particles also have charges. When we look at our three main subatomic particles that we address in this class, we have protons, electrons, and neutrons. And the only one of those that does not have a charge would be the neutron, hence the term neutron. We see in our little picture here, we've got our proton here with his positive charge. We've got our electron here with its negative charge. Now we can actually measure the amount of charge that they have in terms of coulombs, but we don't really worry about that one too much. So generally we just put the proton as a +1, we put the electron at a -1, and that serves our purposes for about 99% of what we do in chemistry. Not just this class, but in all of chemistry. If we look at some of the sizes of these subatomic particles, we can see exactly just how tiny they are and why we choose to express their masses in AMUs. If we look at the protons in terms of kilograms, we see that their masses in kilograms are in the 10 to the minus 27 for the proton and the neutron. If we put the electron in the 10 to the minus 27 exponent, we see that we still have several zeros behind that decimal point. And so it's actually in that 10 to the minus 31 kilogram range, which is very, very small. If we start looking at that in terms of AMUs, we see that our proton is right around 1 AMU. Our neutron is also right about 1 AMU, just slightly heavier out there in the fourth decimal place. For our purposes, we generally say that the proton and the neutron have the same mass, even though we know that the neutron is just slightly heavier, but it's such a small difference that generally it doesn't make any difference to what we're doing. Now, when we look at the electron, we see how much smaller the electron is than the proton and the neutron. Much, much smaller, almost 2,000 times smaller. So it is a very tiny particle. But even though it's a tiny particle, it still carries the exact same size charge as that proton. It carries a relative charge of -1 or 1-, and there we see the charge in coulombs. We see that exact same charge with an opposite sign in coulombs for the proton, and we just say that that is a +1. Now, a lot of times when we're learning chemistry, one thing I've learned is that learning chemistry is a lot like learning a language. And there's lots of things that we do where we use terms that maybe we've heard before in a different context that means something different in chemistry, or we have things that are brand new terms altogether. So let's start looking at some of the language of atoms here. Some of the terms that you see just on a simple periodic table. We see things like main group elements. We see atomic number, we see atomic symbol, we see the atomic mass. We have things like our metals in the main group region of the periodic table, metals that are in the transition area, so transition metals. We have inner transition metals. We have metalloids, also called semimetals, and then we have nonmetals. And then we have all kinds of other things thrown in there as well. We're going to complicate that a little bit and show some terminology that we use when referring to a particular atom. When we want to look at something that is called an isotope, something with a very specific mass number, we tend to write our chemical symbols like this. So our chemical symbol X here would just be what we have as an atomic symbol. So Be for beryllium, Li for lithium, H for hydrogen. So that's what we put in there for that X. Our mass number, A, is the number of protons plus the number of neutrons. And we'll see that down below here in just a second. We have the atomic number. The atomic number is the number of protons present in the nucleus for a given element, and that doesn't change for a given type of element. And we'll see that in our table below here. So if we look down here, let's look at this first symbol here, this 2010 neon. So we see that we have number of protons is equal to 10. If you look on the periodic table here, we see that neon has that 10 sitting right above the atomic symbol. That tells me that it has 10 protons. Every atom of neon that exists has 10 protons. None of them have 9, none have 11, they all have 10. So the number of protons identifies what element we are dealing with for our elements. Let's see here. So that 10 that's down below there in our symbol would go right there. Number of neutrons, notice that's not present anywhere because Here we see that we have 10 neutrons, we have 11 neutrons in this isotope, we have 12 neutrons in this isotope, and nowhere over here do we see 11 or 12 present in that extended atomic symbol. However, what we do see is we see the numbers 20, 21, and 22. And so what we do is we combine these two numbers right here, and that becomes our mass number. Notice that the mass number for neon can be 20, it can be 21, or it can be 22. Okay, number of protons hasn't changed. It still has 10, which means they're all atoms of neon. However, the number of particles inside that nucleus can change because we can change the number of neutrons without changing the number of protons. And notice also over here we have a natural abundance. We're going to talk about that towards the end of this particular section. A lot of different elements have different isotopes, and what they have is a different natural abundance percentage that they occur in. Notice that most of your neon is neon 20, just a tiny bit is neon 21, and then not quite 10% is neon 22. So notice how I said that, neon 20, neon 21, neon 22. This is a different way of expressing which isotope you're dealing with. So rather than use this full atomic symbol, where the atomic number is really kind of redundant because we don't need to show that neon has 10 protons. We know that because it's neon, and we can look it up in the periodic table. However, we do need to know the mass number here because the mass number can change for the different isotopes. And so sometimes what we would say for the neon isotope that has 10 protons and 10 neutrons, so it has a mass number of 20, we would just say neon 20. If it has 10 protons and 11 neutrons, we would say that that is neon 21. So lots of different ways of expressing the same element. Again, chemistry tends to have its own language. So how do we report the atomic mass of an element when we saw that all those isotopes of an element have different masses? You'll notice when you look at the periodic table, you look up neon, even though there's 3 different isotopes, we report just one single mass for the neon atoms. Well, that's because for any naturally occurring sample of neon, all of the isotopes occur at the exact same percentage. And because of that, we can use a weighted average of all of those naturally occurring isotopes to report as the atomic weight or the atomic mass of neon. And we can do that for all of the different elements. So we don't just take an average of what the atomic masses are. So for example, for neon, we had 20, 21, and 22. If we weighed, or if we took the average of 20, 21, and 22, we would just get 21. But if you look at the atomic mass of neon on the periodic table, you would see that it is not 21. And that's because we have to look at a weighted average of each of those isotopes using its percentage. Let's look at chlorine. Chlorine's a good example because it only has 2 different isotopes, and that makes our math just a little bit easier. So chlorine has 2 natural isotopes, chlorine 35, which is present in about 3/4 of all chlorine atoms, and chlorine 37, which makes up the other 1/4. Okay, you can see the percentages there are just a little bit different than that. So the way we write an atomic mass as a weighted average is we convert that percentage that we have here, 75.77, into a decimal, so 0.7577. We take the atomic mass of that isotope, so for chlorine 35, it's 34.97. For chlorine 37, we have 24.23%, so that's our 0.2423, and then we would need to find the atomic mass of that isotope, and it turns out it's 36.97. We multiply that fraction times the mass for each of our 2 isotopes right here and right here. We add those 2 together, and we get 35.45 AMUs per atom, and that is exactly what you see on the periodic table. So here's an example for you to try with gallium. Gallium also has just 2 isotopes, although the abundances are slightly different from what we saw with the chlorine. So go ahead and try that one on your own, and I will post a solution to that one on Canvas. So that finishes out our first section of Lecture 1. You can move on to Lecture 2 once you feel comfortable with this content.